village sizes. Very large batteries can power a submarine or stabilize an electrical grid and help level out peak loads. As of 2017, the world's largest battery was built in South Australia by Tesla. It can store 129 MWh. 41. A battery in Hebei Province, China, which can store 36 MWh of electricity, was built in 2013 at a cost of $500 million. 42. Another large battery, composed of LCD cells, was in Fairbanks, Alaska. It covered 2,000 square meters, 22,000 square feet, bigger than a football pitch, and weighed 1,300 tons. It was manufactured by ABB to provide backup power in the event of a blackout. The battery can provide 40 MW of power for up to 7 minutes. 43. Sodium-sulfur batteries have been used to store wind power. 44. A 4.4 MWh battery system that can deliver 11 MW for 25 minutes stabilizes the output of the Hawaii wind farm in Hawaii. 45. Comparison. Many important cell properties, such as voltage, energy density, flammability, available cell constructions, operating temperature range, and shelf life, are dictated by battery chemistry. 46. Primary battery is chemistry anode, cathode, plus, maximum voltage theoretical, V, nominal voltage practical, V, specific energy, kJ/kilogram, elaboration shelf life 825 degrees C, 80% capacity, months. Zinc carbon zinc 1.61. 2130 inexpensive. 18 zinc chloride zinc 1.5, also known as heavy duty inexpensive. Alkaline zinc manganese dioxide ZNO 21.51.15400-590 moderate energy density. Good for high and low drainages. 30 nickel oxyhydroxide zinc manganese dioxide / nickel oxyhydroxide 1.7 moderate energy density. Good for high drain uses. Lithium copper oxide Licio 1.7, no longer manufactured. Replaced by silver oxide IEC type SR batteries. Lithium ion disulfide Lifes 2 Lifes 21.81.51070 expensive. Used in plus or extra batteries. 337. 47. Lithium manganese dioxide Limo 2 Limo 23.0830 expensive. Use evenly in high drain devices or for long shelf life due to very low rate of self-discharge. Lithium alone usually refers to this type of chemistry. Lithium carbon fluoride Li, CF, Li, CF, N3.63.0120 Lithium chromium oxide LiCrO2 Licro 23.83.0108 Lithium silicon Li 22 Ci5 mercury oxides NGO 1.341.2 high drain and constant voltage. Banned in most countries because of health concerns. 36. Zinc NO 21.61.11590. 48. Used mostly in hearing aids. Zamboni Pilesnag or 0.8 very long life. Very low, nano, Na. Current NGT2,000 silver oxide, silver zinc. ZNAG 201.851.5470 very expensive. Used only commercially in button cells. 30 magnesium GNO 22.01.540. Secondary batteries chemistry cell voltage specific energy, kJ/kilogram, energy density, kJ/liter, comments na CD1.2140 inexpensive. High/low drain, moderate energy density. Can withstand very high discharge rates with virtually no loss of capacity. Moderate rate of self-discharge. Environmental hazard due to cadmium, use now virtually prohibited in Europe. Lead acid 2.1140 moderately expensive. Moderate energy density. Moderate rate of self-discharge. Higher discharge rates result in considerable loss of capacity. Environmental hazard due to lead. Common use. Automobile battery SNIM 1.2360 inexpensive. Performs better than alkaline batteries in higher drain devices. Traditional chemistry has high energy density but also a high rate of self-discharge. Newer chemistry has low self-discharge rate, but also a 25% lower energy density. Used in some cars. NZN 1.6360 moderately inexpensive. High drain device suitable. No self-discharge rate. Voltage closer to alkaline primary cells than other secondary cells. No toxic components. Newly introduced to the market, 2009. Has not yet established a track record. Limited size availability. AGZN 1.86 1.5460 smaller volume than equivalent Li-ion. Extremely expensive due to silver. Very high energy density. Very high drain capable. For many years considered obsolete due to high silver prices. Cell suffers from oxidation if unused. Reactions are not fully understood. Terminal voltage very stable but suddenly drops to 1.5 volts at 70-80% charge. Believed to be due to presence of both argenteous and argentic oxide in positive plate. One is consumed first. Has been used in lieu of primary battery, moon buggy. Is being developed once again as a replacement for Li-ion. LiFePO 43.33.0360790 lithium iron phosphate chemistry. Lithium ion 3.6460 very expensive. Very high energy density. Not usually available in common battery sizes. Lithium polymer battery is common in laptop computers, digital cameras, camcorders and cell phones. Very low rate of self-discharge. Terminal voltage varies from 4.2 to 3.0 volts during discharge. Volatile chance of explosion if short circuit, allowed to overheat, or not manufactured with rigorous quality standards. Performance, capacity and discharge. A battery's characteristics may vary over load cycle, over charge cycle, and over lifetime due to many factors including internal chemistry, current drain, and temperature. At low temperatures, a battery cannot deliver as much power. As such, in cold climates, some car owners install battery warmers, which are small electric heating pads that keep the car battery warm. A battery's capacity is the amount of electric charge it can deliver at the rated voltage. The more electrode material contained in the cell, the greater its capacity. A small cell has less capacity than a larger cell with the same chemistry, although they develop the same open circuit voltage. 49. Capacity is measured in units such as amp-hour, a times H. The rated capacity of a battery is usually expressed as the product of 20 hours multiplied by the current that a new battery can consistently supply for 20 hours at 68 degrees Fahrenheit, 20 degrees Celsius, while remaining above a specified terminal voltage per cell. For example, a battery rated at 100 times H can deliver A device to check battery voltage 5 over a 20-hour period at room temperature. The fraction of the stored charge that a battery can deliver depends on multiple factors, including battery chemistry, the rate at which the charge is delivered, current, the required terminal voltage, the storage period, ambient temperature and other factors. 49. The higher the discharge rate, the lower the capacity. 50. The relationship between current, discharge time and capacity for a lead-acid battery is approximated, over a typical range of current values, by Picard's law, where is the capacity. When discharged at a rate of 1 amp, is the current drawn from battery, is the amount of time, in hours, that a battery can sustain, is a constant around 1.3. Batteries that are stored for a long period or that are discharged at a small fraction of the capacity lose capacity due to the presence of generally irreversible side reactions that consume charge carriers without producing current. This phenomenon is known as internal self-discharge. Further, when batteries are recharged, additional side reactions can occur, reducing capacity for subsequent discharges. After inner charges, in essence all capacity is lost and the battery stops producing power. Internal energy losses and limitations on the rate that ions pass through the electrolyte cause battery efficiency to vary. Above a minimum threshold, discharging at a low rate delivers more of the battery's capacity than at a higher rate. Installing batteries with varying times H ratings does not affect device operation, although it may affect the operation interval, rated for a specific voltage unless load limits are exceeded. High drain loads such as digital cameras can reduce total capacity, as happens with alkaline batteries. For example, a battery rated at 2 times H for a 10 or 20-hour discharge would not sustain a current of 1 am for a full 2 hours as its stated capacity implies. The C rate is a measure of the rate at which a battery is being charged or discharged. It is defined as the current through the battery divided by the theoretical current draw under which the battery would deliver its nominal rated capacity in 1 hour. 51. It has the units H1. Because of internal resistance loss and chemical processes inside the cells, a battery rarely delivers nameplate rated capacity in only 1 hour. Typically, maximum capacity is found at a low C rate, and charging or discharging at a higher C rate reduces the usable life and capacity of a battery. Manufacturers often publish data sheets with graphs showing capacity versus C rate curves. C rate is also used as a rating on batteries to indicate the maximum current that a battery can safely deliver in a circuit. Standards for rechargeable batteries generally rate the capacity and charge cycles over a 4-hour, 0.25 C, 8-hour, 0.125 C, or longer discharge time. Types intended for special purposes, such as in a computer uninterruptible power supply, may be rated by manufacturers for discharge periods much less than 1 hour, 1 C, but may suffer from limited cycle life. As of 2012, lithium iron phosphate, LiFePO4, battery technology was the fastest charging forward/discharging fully discharging in 10-20 seconds. 52. Lifespan. An analog camcorder, lithium-ion, battery life, and its synonym battery lifetime, has two meanings for rechargeable batteries but only one for non-chargeables. For rechargeables, it can mean either the length of time a device can run in a fully charged battery or the number of charge forward/discharge cycles visible before the cells fail to operate satisfactorily. For a non-rechargeable, these two lives are equal since the cells last for only one cycle by definition. The term shelf life is used to describe how long a battery will retain its performance between manufacture and use. Available capacity of all batteries drops with decreasing temperature. In contrast to most of today's batteries, the Zamboni pile, invented in 1812, offers a very long service life without refurbishment or recharge, although it supplies